Welcome to the NPTEL course on computer system optimization for machine learning. Today is the lecture 5. So today we will briefly go through the recap of whatever we discussed in the last lecture, and then we will continue with the convolution of computation. So in the last lecture we talked about mainly talked about convolutional neural network. So remember, we first talked about multi-layer perceptron, right? In the multi-layer perceptron, you have to put all the features in an individual neuron. But then, when we want to classify an image, we shouldn't put in the image pixels as an individual input to the neurons, right? That's why this multi-layer perceptron treats each pixel in an image as input to a separate neuron, right? But then it misses the spatial similarity within an image. So remember, when like as a human being, when we try to classify an image or when we try to understand an image, we see the spatial similarity between the pixel or the neighboring pixel, right? And that's why this convolution capture information from the neighboring pixel, and that's the main reason behind the huge success of this convolutional neural network. Now, if you remember, convolution operation is very simple. We just need to slide a small matrix of parameters which is known as filter across the input image, and then we need to train the filter using backpropagation, right? At some point we will probably discuss more about the training also. Yeah, we discussed this briefly in the last class. Modern deep CNNs typically have like 5 to 1000 layers. I mean, you will always ask this question, like how deep is actually deep. So anything beyond 5 layer or beyond 4 layer is called as deep CNN. Now there are multiple layers of for this convolutional neural network. Now, as we discussed in the last class, that first few layers capture the low level features. Like if you see an image of human face, then probably first few layers are capturing the edges, brightness of the image, intensity of the image or intensity of the pixel, and so on and so forth. And then the last few layers capture the high level features like nose, eyes, ears, which defines a human face. And finally there is a fully connected layer which classify the image into multiple classes or the intended classes. Now we also discussed about convolutional layer, like how this convolutional operation going on. So remember, we have these we have the multiple of these filters. Each filter size is R by S by C, and then remember, why do we have C channels in the filter? Because in the input feature map we have C number of channels, right? Now this input feature map size is H by W. So since we have M number of filters, that's why we have this M number of channels in the output feature map, right? So each of the filter will correspond to one plane of the output feature map or one channel in the output feature map. Since we have M filters, we have total M channels in the output feature map. Okay. Now again, when we do this inference, we will see that we typically don't do an inference of just one image, we do an inference of batch of image. Now let's say in one batch of image there are total n images. So if there are total n images, then of course we want n outputs. So that's why we have these n outputs, right? That's what we discussed in the last class. And then we also, this is just a summary, like we have filters which are 4 dimensional, R by S by C M, S by C by M. R and S are the height and width of the filter respectively. C is the number of channel and M is the number of filters, right? Then we saw how to implement a convolutional layer. I will not go into the detail, but you can see that we have a 7 layer for loop, right? So the for loop goes like for n equals to 0 to for n equals to 0 n less capital N, where this is the number of images in a number of images per batch, and then we have for m equals to 0 m less than m, this is the number of filters which will also be treated as the number of channels in the output feature map. Then we have E and F, these are the dimension of one output feature map, and then we have this R by S, which are the dimension of filters, and then we have C, which is the number of channels in the input feature map, number of channels in input feature map, right. So this is, I mean, you have to loop across all these dimension, and then only you will obtain the convolutional output, right. So again you can see that this B of M is there. B of M is nothing but the bias term. Okay. And then finally you can see that we are accumulating across one filter. So you can see that output of NMXY is nothing but input of NK, and then this term defines the slide. So if you remember, sorry, not slide, sorry, stride. This is something called stride. Like if you remember, when we were convolving one input image with one filter, we can make any number of stride to perform the next convolution, right. So this ux and uy, uj, uy is nothing but the stride length. So that's what we discussed in the last class. And now let's see how this, I mean, okay, that's the algorithm. That's how we can implement a convolutional operation in a naive way. But is there a better way to implement? So remember, whenever you write this 7 layer or like 7 layer nested loop or 7 layer for loop, then see, at each and every step you have to what should I say? I mean, you have to access all those memories, right? All those memory elements. So if you have like all like long for loop, then the number of memory accesses can be more. Also remember, the accesses are kind of irregular. So let's say we use this R by S by C filter that got convolved with this part of the image, and then again when we go to the next part of the image, the same filter will get access from the scratch. So these are some opportunity where we can do some optimization. So let's see one such opportunity of optimization. So just as a recap, let's say we have a filter of size 2 by 2. These indices are nothing but the index of the filter 1, 2, 3, 4, and then again let's say we have an input feature map of size 3 by 3. Again, the elements or the entries are the indices of the input feature map. Those are not the exact values. Okay. Now if we convolve this 2 by 2 filter with the 3 by 3 input feature map, then we will, which is, let's assume that the stride length is 1, then we will obtain our output feature map of 2 by 2, right. Now let's see what are the steps. So again we have this filter 1, 2, 3, 4, and then first it will get convolved with this particular portion of the image with these indices 1, 2, 4, 5. Remember, the convolution means the element wise multiplication, right. This 1 will get multiplied by 1, 2 will get multiplied by 2, 3 will get this multiplied by 4, this 4 will get multiplied by this 5, correct. And then the first pixel of the output feature map will be obtained. So if you look closely, we are actually performing a dot product, right. If we flatten this 1, 2, 3, 4, this particular kernel into one vector, then we will get this, and then this row vector is actually getting multiplied with this column vector, which is nothing but the flattened version of the first patch of the input image, right. So this 1, 2, 3, 4, these 4 elements will get multiplied with these 4 elements in an element wise fashion, and then they will get added, right, to obtain this first pixel of the output, correct. So similarly, if we have the same flattened filter multiplied with the next patch, which is nothing but 2, 3, 5, 6. Why 2, 3, 5, 6? Because since our stride is 1, the next patch is nothing but these 4 pixels, correct. So if we do that multiplication, again we can flatten that 2, 3, 5, 6 into one column vector, and then we can perform that element wise multiplication. After that we can add all those product to obtain the second pixel of the output feature map, right. So as you can see, if we flatten this input feature map as well as the filter, then we can actually represent this convolutional operation as plain vector multiplication, right. So, as I already told, this 1 2 3 4 is getting multiplied by this 1 2 3 4 to generate this first pixel in the output feature map. Then again this 1 2 3 4 is getting multiplied by this 2 3 5 6 to generate the second pixel in the output feature map, and so on and so forth, right. Now, if you look the overall picture, I mean we have we are performing vector multiplication to generate one pixel. Now, to generate all the pixel, we have to perform vector matrix multiplication. So, the first vector is nothing but the flattened version of the output, flattened version of the kernel, the filter, and then the matrix is nothing but the flattened version of the input feature map. So, the each of the column represent the flattened version of one patch of the input feature map. So, the first patch corresponds to this 1 2 4 5 these 4 pixels of the input feature map. The second patch corresponds to these 4 pixels of the input feature map 2 3 5 6 and so on and so forth. Now, if we perform the matrix multiplication of this vector 1 2 3 4 and this particular flattened matrix, then we will get all the pixels of the output feature map, right. So, hopefully it is clear. Now, remember that we do not have or before that, before going to that part. So, what we just did is, I mean this is the filter, this is the input filter 1 2 3 4, and then this is the input feature map where we have 9 pixels. If we convolve, then we get this out as output feature map, right. That is the regular convolution operation. Now, in this flattened version, what we did is we flattened this filter in a row vector format, and then we also flattened this input feature map in a specific way, so that each of the column vector represents one patch of the input feature map, right. Now, if you look closely, some data is repeated, like this 2 is repeated, this 4 is repeated, this 5 is repeated, this 6 is repeated, and so on and so forth, correct. So, some data is repeated, right. Now, as I was saying that remember we do not have one single channel of the input feature map as well as the kernel, right. We have multiple channels, correct. So, that is why in this case also you can see that we have same this 1 2 3 4 of channel 1, and then we have to have the same dimension of the kernel for channel 2 also. Okay. Now, why do we have 2 channels in the kernel? Because we have 2 channels in the input feature map, right. Remember, the number of channels in the input feature map has to be exactly same as the number of channel, or other way around, the number of channels in the filter has to be same as the number of channels in the input feature map. So, that when you do the convolution, you can actually perform the channel by channel convolution and then add them up, right. Now, yeah, as I was saying that if we have multiple channels, if we have 2 channels, then the first channel will get convolved with this first channel of input feature map, and then the second channel of the kernel will get convolved with the second channel of the input feature map, right. And then both the channels, or both the convolutional output from both the channels will get added to obtain this output feature map, right. That is the one channel of the output feature map, because we are just talking about one filter, right. That is why we have this filter 1 here. So, and again the key is if we have this entry in black, that is the input channel 1, and if we have entry in yellow, that is the input channel 2, right. So, yeah, both channel 1 and channel 2 in the left are used to generate channel 1 of the output. Okay. Now, in this case, like remember when we had like one channel, right, when we had one channel, we could flatten the kernel as well as input feature map to like flatten the whole convolutional operation into just matrix vector multiplication, right. Now, if we have 2 channels, then how can we do the flatten? Let us see. So, in this case what we need to do is, so remember if we have just one channel, we just had this one 1 2 3 4, and then we just had this one channel of input feature map, right. Now, if we have 2 channel, then remember all the filter values corresponding to the channel 1 has to get multiplied with the input feature map corresponding to the channel 2, right. So that's why we have to align the filter, the flattened filter as well as the flattened input feature map in such a way that the input the filter values of channel 1 gets multiplied with the the values of the input feature map in channel 1, right. So the first part is very clear. For channel 1 we have this 1 2 3 4 and then we already saw this flattened input feature map, right. Now if we append the channel 2 in column wise, I mean in the next columns, and then append this channel 2 of the input feature map in the subsequent rows, then you can see that this 1 2 3 4 will get multiplied by this 1 2 4 5, and then again this 1 2 3 4 will get multiplied with this corresponding channel. So remember, this is a channel 2. So this channel 2 filter values or the kernel values will get multiplied with this channel 2 of the input feature map, and then all of them will get added, and that's what we want. So remember, all the channel values or all like whatever we are getting output from the convolution operation from each channel, they have to be added up to get the final answer or the final result, right. So this 1 2 3 4 will get multiplied element wise multiplied with this particular channel of 1 2 4 5, and then again the next channel filter values will get multiplied with the input feature map from the next channel, right. And then since it's a vector matrix multiplication, everything will get added up. So we get the first pixel of the output feature map, and similarly again the same this appended channel will get multiplied with this second column to get the second pixel of the channel 1 in the output feature map. So the beauty of this thing is, since we are appending this channel in the same row and we are appending the filter of the channels, filter values of different channels in the same row, and then input feature map of the different channels in the same column, they automatically gets added up to produce the pixel of the channels, right. Now again, I mean, as you can see that the computation is vector matrix multiplication, right. So you can flatten both the filters and the input feature map to obtain the output feature map pixels, correct. Again, remember, we do not have single filter, right. If you remember that in our example of convolutional operation, we are saying that we usually have m number of filters, right. If we have m number of filters, then we have to have m number of channels in the output feature map, right. So far we just had one filter, right. Since we have just one filter, we just have one channel in the output feature map, correct. Now how should we treat or how should we do this flattening if we have m number of channels, m number of filters? Let us see that. So as a quick reminder, so if we have m number of filters, then this is the, let us assume that we still have two channels. This is the filter 1 and this is the filter 2. If we see that there is underline, then that means that is the filter 2 values, right. The input remains the same. So remember, the filter can be there can be as many filters as we want, but then that does not hamper the input. The only constraint is the number of channel. If we have c number of channels in the input, then we have to have c number of channels in the filter, right. So that is why the input, there is no change in the input. There has to be two channels in the input. Now since we have two filters, so remember, if we have m filters, then each of the filter will contribute to one channel in the output feature map, right. That is why since we have two filters here, we have to have two channels in the output feature map, correct. And that's the reason you can see that we have channel 1 and channel 2 of the output feature map. If you see the underscore or the underline in the numbers, that means they are getting it from the filter 2, right. The outputs are generated from the filter 2. Now remember, again I am telling you again and again that these numbers just denote the indices, they do not actually denote the exact values, right. Now so this is the example of multiple input channels and output channels, right. Now how should we flatten the input and the how should we flatten the input feature map as well as the kernel, so that we can just do a matrix or we can just do some vector matrix multiplication. Let us see. I think you have already imagined that we should be doing in this way. So, when we just had one filter but multiple channels, then we appended the channels in the same row, right. So, we appended in the same row to obtain this flattened version of the filter, correct. And then since we have multiple channels, and then both of the channels need to get multiplied with the corresponding channel in the input feature map, we stack this input feature map in column wise, like vertically on top of each other, right. That gave us the first channel. Now, again for the second channel we have to do the same operation. So, we have to append the second filter, I mean for the second channel to get the second channel in the output feature map, we have to do the same operation. Same operation means we have to do the same convolution operation, but with filter 2 values, correct. So, that is why we are appending this filter 2 values in a different row, okay, in the next row. Now, if we do that, that means these filter 2 values, these values from filter 2 will get multiplied with the same input to obtain another channel, right. So, since if you just remember the basic matrix multiplication, you will understand that first these values of the channel 1 will get multiplied with all these to obtain this channel 1 output feature map values, and then we will go to the next row and then perform the same vector matrix multiplication to obtain the values of the channel 2, right. Now, that means we can actually flatten both filters and input feature maps in the same way as before. That will naturally generate the flattened output feature maps of 2 channels, right. Now, here what did we actually gain? So, remember when we did this typical convolutional operation, or when we introduced this typical convolutional operation, we had that 7 layer for loop, right, which is like difficult to write, and then we will go in detail later. But then if you think about memory access, like for each of the for loop we are accessing some memory, right. For each of the for loop we are accessing some value from the cache or the main memory, right. Now, instead we just have a matrix multiplication. Now, for 2D matrix multiplication, you can just write it as a 3 layer for loop, that is all, right, for I equals to, or 4 layer for loop, that is all, right. So, now you have from like 7 layer for loop, actually we have reduced the whole computation in a matrix multiplication, which is much simpler than the convolutional operation, right. So, that is one of the optimization we can do. But then remember, before this matrix multiplication, we have to flatten, right. So, nothing is free when we are executing something on our computer, nothing is free. So, that flattening will take some time, and then remember we have these channels. When we are getting the outputs, we are actually getting this flattened output, right. We are not getting like nicely shaped the output feature map, because remember this 1 2 3 4, again it has to be like this 1 2 3 4 as one channel, and then another channel has to be this 1 2 3 and then 4, right. We have to arrange that so that the next layer computation can be done. So, there has to be some pre-processing and then post-processing. So, not necessarily every time if we do the flattening there will be benefit. If this pre-processing and post-processing takes lot of time, then we will not have any benefit from this flattening exercise, right. So, just as a reminder, when we have this convolutional computation, if we do the flattening, then again this RSCM is nothing but where R and S are the height and width of the filter, C is the number of channel, and M is the number of filters, right. When we do the flattening, then we are flattening this filter by CRS by M. So, remember we stacked all the different filters like in multiple rows. That's why we have this M. CRS, the number of channels as well as the R and S were flattened in the same row, correct. Then we have this input feature map. So CRS will come here, because remember, if we are doing matrix multiplication, right. So if we have CRS number of columns here, we have to have CRS number of rows. And this particular formula shows that if we have input feature map of height H and W and the filter size of R by S, then if we have stride of 1, then and then if we have number of images as n, then you will get the number of columns of the flattened input feature map, and that will give us the this output feature map, right. So that's all for this lecture, and in the next lecture we will see some nonlinear operation and then some more details on computation of this convolutional layer. Thank you very much.